want to share my screen. All right. Welcome everyone to the third circle of Straxferno. So today we've got quite a few items on our agenda or plan. First, let's finish the presentations on the homework that you guys have been doing on the different Strax algorithms. Then I'll give a very brief reminder of just where we are in the course and have just a short demonstration of different mini analyses. And then we can get into the assigned reading and any questions that you had on those. And we might have a short preview next week afterwards. Okay. So let's load up the algorithm slides. Here we go. This is where we left off last time. Let's see, we have baseline, find hits, cut outside, integrate, lone hits, some waveform, and that's where we ended last time. Okay, so we've got split peaks, another peak splitter, peak merging. It's good, it happens after peak splitting. Peak property computation, and then we have here touching windows. Yeah, okay. No, I think that looks good. So let's see, Joran, do you want to start with your slide on split peaks?
Sure. So split peaks is for splitting peaks, and in doing so, it creates peaklets rather than peaks. So how do we end up with peaks in the first place? Well, we do the hit finding first, and then we look for gaps in between the hits and those regions where there are a lot of hits, followed by a region where there are not so many hits, are made into the first kind of peaks. However, these peaks can be actually a bunch of peaks bundled together. That's what you, for instance, see in waveform 1, where you could say that there are probably 2 peaks in this one peak. And for that, we do the peak splitting. If you look at the second waveform, you see that after the splitting, there are actually now 2 waveforms, 2A and 2B, which are individual peaklets. Now, whether these peaks should be 1 or 2 is not so relevant at this moment, because that will become clearer when we are talking about merge peaks from Robin. But this is basically what happens at this function. So how does this work? If you look at peak 1, we compute certain criteria. For instance, whether it is natural to break via the natural breaks algorithm that Joey will describe in the next slide. And if so, if this criterion is matched, we do split peak 1 and create 2A and 2B. Well, this can happen multiple times. For instance, if you look at 2B, you might say that it even consists of more peaks. So it does this iteratively until either we have done 20 splittings or we are getting peaks that are so small that it doesn't make sense to split anymore. And I think that is what happened at 2B, that if you try to again split that peak, you become under this area threshold. Now, also notice that we do recompute the sum waveform, and why this is important is trivial to all of you, given the presentation by Daniel last week. And if it's not so trivial, you can look at the backup slides why it's important. So yeah, it's used when we make peaklets, and how it's exactly done will become more apparent in the next presentation when Joey is talking about the natural breaks algorithm. At the moment, it's not tested, but I see Tim is actually working on adding a test, so that's actually good news. So yeah, that's what I wanted to say about splitting peaks, which allows us to from the first temporary peaks we make, decide whether actually they're consisting of multiple peaklets rather than one big peak.
Thanks, Joran. Any questions to Joran about split peaks?
Yes, but this is maybe a very, I don't know, minor question. So I was also going through the algorithm and I saw that I think in line 70 we compute with the widths of the new peaks, and I was really wondering
Daniel,
why.
just let me get the algorithm that we're looking at.
Yes.
So it's in peak splitting in Strax, right?
Yes.
Okay. Peak splitting.
Exactly. And I
Strax,
think
it's
line
here.
70.
Line 70.
Exactly.
Yeah.
We compute there again the widths. So I was wondering, why do we do this within the algorithm and not just doing it once after we computed all the peaks, meaning the old one and the new split one? Because I didn't discover where in this algorithm we would use the width. So I was really wondering why it's in here and not just afterwards.
So I think that this is because we do this iteratively, and at some point you stop, but you still want to have the new peaks, this property. And they, of course, are not the same as the peak you had as to begin with. For instance, if you looked at peak 1, that obviously has a different width from peaks 2a and 2b. So you do want to, in the end, have the width of the new peaklets.
So you keep also peak 1. You just not produce out of one peak 2a and b. You also keep peak 1.
No, you don't keep peak 1.
So yes, then you can also do it afterwards, right? First you split everything to 2a, to b, whatever, and then you compute the widths of all the remnants. Of all these 2a to b, and so on and so forth.
Yeah, I think you're right. I think you can certainly do it again at the end. I mean, if you have a new peak, then it should work. And if it's not used as width in the clustering, you don't really need to do it here, because it depends on how many peaks are split. If you do it here, you don't know which peaks are new anymore.
Yes, so no, I'm talking now if you go to Strax and peaklets.
Okay.
We are doing the very same Strax compute widths just right before we call this peak splitting. And so I was really wondering, because I'm trying
Sorry,
to
Daniel, where do you want to go?
A bit further down, I do not know the exact line. Yeah, I think it's...
Split peaks?
Yeah, exactly. And just above you compute the width. Just above?
Yes.
Exactly. So what you could also do, you could split peaks and compute then the widths for all peaks afterwards. So it says somehow these are properties needed for the algorithm, but I was not able to see where it is needed.
Okay.
I guess I'll have something to say for that. Like, you can see when you look at the individual algorithms like natural breaks, some instances where the widths get used, right? So it's just so that you have access to that information in whatever algorithm you make to split a peak.
Yeah, that comment here certainly implies that. It's great that if you can clarify that, Joe. Yeah, I didn't remember whether we used it, but I think
it's to build a threshold, right?
Yeah, that's right. Yeah.
Can you point me to the line, because I was really not able. If you don't know it by heart, I would try it again, but I was really not able to find it.
So it should be a natural base splitter.
It might be in Straxen where you used it.
Yeah. Here, the thresholds. Natural breaks thresholds. That's it. Here you go, area decel from midpoint.
Okay, thanks.
Yeah. Yes, there's a threshold function that's separate from the peak splitter itself that you pass to the peak splitter. And that you can make however you want. And in this case, it was used to get the width.
Okay, thanks.
Yeah. Okay. Yeah, it was an interesting question. Any other questions? So maybe before we go to Joey's presentation, it'd be an idea to briefly look at Tim's pull request, because I think it's a very nice one on just adding a test. I don't know why it's asking me to. So Tim, maybe you could briefly say something about your pull request. If you want to share the screen, it goes to any of you, just tell me and I'll stop sharing.
No, it's fine. I think you can do it.
Okay.
Can you hear me?
Mhm.
Okay.
Yeah.
So in principle, the idea is first I went through the code of local minimum splitter, I think it's called, and I tried to understand what the output of it is. And the output is essentially the indices where the peaklet should be splitted, or the peak should be splitted. And so then I applied some tests of what numbers can be returned from. I mean, essentially it's a list. It's not a list what it's returned, but a generator. But you can use this list as a generator. And so here in line 6, I define this instance of local minimum peak splitter, minimum splitter. Then I import this normal splits variable, which is essentially the value of the last item in this list, and it's also the smallest number. Then this minimum height and minimum ratio are essentially 4 arbitrary settings for the local minimum splitter. Then this W is then I mimic a peak. It's just a list of random numbers, and then I loop through the settings that I have chosen there. I get this object my splits, and then I do some checks with this my splits. I want to have it in an array. It's a generator, so I make it a list out of it and an array. So by the way, if I do something stupid computationally or Python-wise, please point out to me. I'm not an expert in this. But then, in any case, I use this assert statement in line 25, and the length of it is always bigger than 1, because even if there's no split found, it returns this variable which I defined up there as the last item. Yes, and then I try, so essentially I get back the minima for these indices. Then I look left and right of these indices. So I take one before and one after, loop over it. Then I leave out the last 2 items, because the very last item is this dummy indice that you know that there are no more splits. And the next to last item is just the last indice, so it's not a true minima. And then I loop over it and I check if left and right are bigger or equal to the minimum, because this is how the minimum is defined. So it checks whether left and right from this minimum is bigger or smaller. And this I do for all these configurations. Then in principle, if you were unlucky in a certain sense and you would have the maximum number of minima, the first index cannot be a minimum, because you want to have a maximum before it, and before is nothing. And the last item, or the third to last item, cannot be a minimum. Okay, it can be a minimum, but if you do the math in line 39, this is essentially the maximum number of minima that you can get from a peak series. Then the last item should always be this no more splits, and I don't understand what I did there. Okay, the minimum of all of these items should be no more splits, because this is the placeholder for looking where no split occurs anymore, and it should be the last item. And these are the splits that or the checks that I did until now for this, but of course one can come up with more sophisticated and more secure checks that what is done makes sense. If I look at it now, probably would make sense to have an assert statement that the first index not a 0. But in principle, this is the idea, that you get these indices and you perform some basic checks on them and see if what is returned is sane.
Okay, thanks, Tim. So at least I don't remember exactly how the algorithm worked well enough to understand the code just as I'm seeing it. But I think it's very valuable for people to see just how a test like this works and sort of the general things that you're doing here. So you're running an algorithm over a random input, and then you're asserting certain properties that have to hold. Like no matter what the input is, it has to have, it has to be a length larger than 1. It has to have various other properties. So that way you really test various cases of the algorithm. So that's very nice.
Yeah, and exactly. So one could come up with more and more stringent tests if one wants to, but this is what I came up with until now.
Yeah, thanks, Tim. Any questions to Tim?
You might be able to loop over the algorithms. It seems like all the things you tested are agnostic with respect to the algorithm. So I think it could be natural breaks too, and all these things should hold. So that would make a test not just local minimum, but the other guy.
I can try this. Yeah.
Maybe you have to also then keep track of which options you need for both. But other than that, I think it should be completely fine.
Yeah, no, sounds like a good idea. I don't know about this check that there is a local minimum, whether that's always satisfied for natural breaks, but I guess we'll see soon enough when you try it. Maybe I've got one question for you guys. So in general, when you write unit tests, something like this is often discouraged. So having a random input can give problems. Can you guys think of what problem that could be?
That you cannot replicate the failure.
Yeah. So that is a problem. There can be a failure that occurs sometimes. For example, maybe there's only a failure if this is all zeros. Now, okay, with 100, you can essentially, that's never going to happen with floats. But you can imagine other things that sometimes cause a failure. So what that will then manifest as, your pull request will run fine because it usually doesn't fail. But then a month later, somebody else will make a pull request and then that will mysteriously fail. And we look at it and say, oh, there's something in the peak splitter, but hey, you're not doing anything with the peak splitter. What happened? And then they make a commit, changing a comment, and then it works. And if there are several of such tests, it can get quite frustrating.
I understand your point, but what would you do then? You just add a list of values, which is hard-coded in there?
So I don't think it should be discouraged. I think it is fine to test with random inputs. But there are ways, it's fine as long as you test all of them, basically, as long as you, or test a very large set of them. So we have some tools for that in Strax. They're based on the hypothesis package. So, let me just show you some of these tests. They're in tests, right? Let's see, pulse processing. So here we have some tests for the hit finder. So yeah, one thing is what you mentioned, Tim. You could just have a list of possible inputs and then outputs that you should give, or a list of possible inputs and then do your assertions. Or you can use hypothesis and tell it to randomize the pulse or the window width or everything. And it will then try, I don't know, hundreds or sometimes thousands, depending on how many you put in different settings. If it finds a failure, it will automatically reduce it for you until the case where it actually fails. So let me try and quickly introduce a bug in something and just show you how this works. Okay, so let's actually introduce a bug in, let's see, take an algorithm. Okay, we were looking at the hit finder test, so let's go to the hit finder. It says pulse processing. And let's return, let's see here. Let's do hit start -3. And multiply this by 2. This -1. I just want to be sure that it's going to catch some bug. It's going to be embarrassing if I make all these modifications and nothing happens. Okay, now surely this must crash, right? So now I can do PyTest, and it will run a variety of tests, and it should find then some kind of case where it fails. So it'll first run some tests on like core functions, which work fine. It would have run Tim's test if we would have merged that already, and that should then also have passed. Here's a test that takes long, and that actually fails. That's interesting. Maybe it calls find hits. We'll see in a moment. If you don't want to wait for the output of these kind of tests, you can do -x, and it will give you only it will stop as soon as there's a first failure. So now let's just wait, it's almost done. And I'm just spending a bit of time on this because these unit tests are really important. They give you the confidence to go into an algorithm and change something. If it's not tested, then yeah, maybe it works after you've changed it, but maybe it doesn't, and it's just really difficult. And in Strax, there are a lot of unit tests. In Straxen, there are essentially none. So that's a great place to extend. Here we go, test pulse processing fails, so that's good. Right, so now you see here, test find hits randomize. It says, yeah, you failed here on this assertion error, and this is the falsifying example that will provide it. So hypothesis randomized many things and then reduced it to an example that will fail. This you can then report or try to fix. So I think random numbers are fine within tests. In this case, you know, certainly having this test is way better than having no tests. But one way to improve it would be to use hypothesis to try many random waveforms and many variants of these settings. If you're going to try only a fixed amount, you can do a different kind of tests where you specify the exact output that you want for each example and just check that that doesn't change. Those are just some general tips. I think it's great to add unit tests like this, and I think you're the first person to do so. Sorry if I'm offending anyone who did add one and I forgot at the moment, but this is very good. Okay, other questions to Tim more about unit testing? Then I propose we move on. Let's go to natural Blake splitting. Joey.
Yeah, hey, so this is an example of one of those peak splitters, and we use it in our current clustering algorithm. So essentially, we want to break down, when we make these peaklets, this peaklet plugin, we want to give you back kind of the largest number of peaklets there's going to be, because after this step, there's only merging. So this is one of the algorithms that does that, with a dedicated goal, mainly to separate these krypton S1s, which are very close together and difficult to cluster correctly. So those usually will appear as something that's kind of bimodal, but not so well resolved. So what you want to do, or what this algorithm does, is you want to decide, you have some peaklet and you want to decide whether there's really multiple peaklets there. And the way you do that is by defining some statistic that quantifies how splittable the peak is. And that's this goodness of split statistic. So 3 of these choices of that statistic are plotted in these 2 examples on the right. The algorithm calculates the statistic at every position in the peak. And then if the statistic ever exceeds some defined threshold, then at that location, or at the highest location, you split the peak into two. So that's supposed to reflect the point in the peak at which it's most happily two peaks rather than one. So there's different versions of this statistic that can be used. There's this default is actually not used in the current Straxion. It's the default of the Strax algorithm. And it's just to consider the variance on the left and right of that split point, potential split point. The second one is if you normalize those two variants. And the third is the same thing, but you penalize based on the height of the location you're considering. So it prefers splits at more minimum like things, at lower amplitudes. So that third one is actually what we use currently in Straxon. It's because I think it's doing this natural breaks thing while also having a hint of the local minimumness in it. Because it prefers these kind of lower points. You can see that kind of in this top one where the purple guy kind of shoots up right in the middle. Yeah, so that's the idea. It's called in Straxon inside the peaklets plugin. And this threshold that you define for when to make a split or not, it can depend on the other statistics of your peak. That's to answer Daniel's point. So that's the line that Jelle found, where the threshold that we use actually depends on the rise time. And in general, it can depend on rise time and area, I think. Yeah, then the idea is, yeah, you can look at all these nice PRs that have more plots like this to show how it gets used. But the main idea is to break up Krypton S1s. In the process, you're gonna chop up some kind of dispersed deep S2s. But the idea is that anything you chop up that you're not supposed to gets merged later. Yeah, that's it.
Okay, thanks, Joey. Any questions about the natural break splitter?
I have one out of curiosity. So I guess we are using it for S1 and S2s, and I would also like to use it for the neutron V2, but for the neutron V2 we have just PMT pulses, which is kind of similar to S1s. But do you think it makes sense to use this algorithm, or do you have any indication that it doesn't make sense for S1 or PMT-like signals?
I think it can work on anything, but you might have to retune your thresholds or use it in a different way if you're, I don't know, Jelle should say.
Okay, yes, this for
I
sure.
also
This I
don't know.
expected.
Yeah, give it a try. I don't know. And the only reason it really wouldn't work is if, for example, it was too slow, because it's meant to work on peaks, which there are far fewer than PMT pulses. But I don't think it's very slow. Okay, other questions? Then let's move on from splitting to merging. So Robin, can you say something about merge peaks?
Yes, hi, do you hear me?
Yes, I hear you.
Perfect. So what merge peaks does is it merges peaklets of S2 type, which is used in peaklet processing. It takes as input candidate peaklets that you want to merge, and you're giving already from other Strax functions or methods the start and end index of peaklets that you want to merge. And you also give a max sample of the sum waveforms. So how many samples you want maximum per waveform, and the output is going to be peaks. Yeah, actually, the code is pretty straightforward. So we just use the peaklets that we're given and extract all the fields that we want, like channel here. To be honest, I'm not sure why we have a channel which is a index here, an integer here. something because further down we can see the saturated channel, and it is giving us not only one PMT, but we see the peaklet in possibly all of the PMTs, but we are only assigning one channel. So this, I'm a little bit puzzled about that, but other than that, it's pretty much just assigning the start time, for example, of the first peak, then the end peak of the last peaklet, and the waveform is the special thing here. You get the greatest common denominator of the dt and store the data that you get from the peaklets in a buffer, and then it gets downsampled by another Strax function, and then you end up with the sum waveform. And yeah, I think that's pretty much what it does.
Okay, thanks, Robin. Any questions to Robin?
I have one. Hi. So sure,
just
it's yeah.
Your connection is a bit unstable, but go ahead. Just try it.
I'm sorry. Okay, let's try. If it's possible to merge in these peaks, also some peaks that were of type S1 previously, so they get merged in S2. Is it the case?
I guess you could, but I think what's actually the case here is you get so wide peaks that they're split up in peaklets, and then you want to merge them, and S1 is not that wide as I'm aware. So you don't need to merge them since they're only in one peak already.
S1s can get merged into other things as long as they're not the first constituent. Currently, that's how it's done, I think. So like if you have an S2 and then an S1 really close after it, Andrea, then it will get merged into a single S2. But if it's an S1 and an S2 right after that, they won't get merged.
Oh, okay.
Yeah, so maybe it's good just to remind ourselves why we're doing this, so that you may wonder why we're splitting it and then merging it again. So the nice thing is that here we try to split it into many different peaklets, then save that to disk so that it really split as widely as could sort of possibly make sense. And then in this merging step, we can apply any kind of complicated algorithm we want. We can change that often, and we can reprocess then starting from only the peaks. And the peaks are, a factor 30 or something less in total volume than the raw data, which means that likely this can stay on the analysis facility, whereas the raw records and so on cannot. So if we fix these two algorithms early, then this one we can keep modifying until we go crazy, basically, and we can make this as complicated as we want and think about all these cases with, well, if you first have an S2, then an S1, and then an S2 that looks weird, etc. Maybe just to the question you raised about channel, that's really an artifact. It's I think in PAX we had the idea that lone hits could also be peaks. That's not the case in Strax, at least not now. For lone hits, then it would make sense to assign a channel. For peaks with many channels, it clearly doesn't make sense. You can register which channel has the highest hit, for instance, but that's a separate field in another thing. So I think we just set it to -1.
Oh, right. Okay.
Yeah.
Thanks. And then one thing I would like to mention is here for the tight coincidence, it is described as hits around the mean, and if you combine the peaklets again, that's not true anymore. It's like it's not the mean around the mean anymore if you just combine all the tight coincidences, right?
Yes, that is true. So we'll have to see exactly what it says, but yeah, tight coincidence will be a variable that you would have to go back to the raw data to get. So in that case, I think, so do we take the tight coincidence of the largest peak, or what do we currently do?
I think we use the mode because that's something you can get from the constituent peaks, right? I think maybe the word mean is incorrect. I can check what we did. Am I wrong? Somehow you build this from the constituent peaklets.
We're using the peaklet with the highest, with the maximum amplitude, and yeah, the type coincidence.
Yes, there's two issues. There's one is like, how do you build it in the first place? And the second one is, okay, given that you build it for all peaklets, how are you going to assign it for a merger of many peaklets? And I think it will make sense indeed if you have the mode, maybe, or honestly, I don't remember. But here, yeah, all you can basically do is take one of them or sum them all up or something like that, because you don't have even hits anymore.
And then
we also try to compare the mode and the mean, and it seems to be more complicated than we thought. And if you use a different algorithm, it will probably have a different feature. And sometimes it's accept more background, sometimes it's reject more background. So you can all experiment with different algorithms. And
yeah, good point.
And if you don't mind, I get like this little questions thing here. It's some of the comments got me to these questions actually, because the buffer is re-zeroed for every iteration over a new window of indices, basically. And this could be, I don't know actually what the constraints from peaklets are, and we're just depending on our premises, we can improve that a little. Down in the comment box, I wrote a little something like that.
Okay, thanks for looking into that. I guess we'd have to really look at the code to see what the buffer means, etc., before we can do that. But on the first one, at least, I can reassure you that peaklets don't overlap. That if that happens, then there is a problem. We should crash immediately. That won't happen.
Yeah. Great. Good.
Okay, thanks, Robin. So let's move on to computing properties of this peak. So let's go to index of fraction. Andrea, you tell something about that.
Here I am. Let's hope my connection works. Let's try. Yeah, so the goal of this algorithm is to calculate the indices, the position at which the peaks reach a certain fractions of their total area. So you need as inputs the peaks, of course, so it's an array of peaks or peaklets. And then an array with the desired fraction of the area that you want to, for which you want to know the point they are reached. So it's a list of numbers between 0 and 1, float numbers between 0 and 1. The outputs that you get from this algorithm is for each peak, the fractional indices. So it's a float number, which tells you at which sample the peak reaches the fraction of a certain fraction of the area. An example will show you how it works. So you can see this figure, an example of one peak with its different samples. You see on top the sample index, it's an integer number from 0 to 5. And then the red numbers inside the sample reports the fraction of the total area, which is inside each sample. So, and then let's suppose we want to know the following fraction of the area, 0.1, 0.5, and 0.95 of the total area. This is just an example, of course. You can choose any other number. So for each peak, we move sample by sample. We check if the accumulated area passes the fraction desired that we are currently looking for example, 0.1. And if this is the case, we can calculate the position inside the sample in which this happens. For example, you can see 0.1 is reached inside the sample 0, and particularly the result will be 0.66. So this is the fractional index at which 0.1 of the total area is reached. And then once this is calculated, you can move to the next fraction desired, so the next value, which is 0.5 and then 0.95. And this is done for for every peak. One note, for this algorithm to work, it must be total peak area greater than 0. And a comment in the algorithm says that sometimes it happens, it is not the case. So of course, if we have a peak whose total area is lower equal 0, the outputs will be a list of 0. So we don't have any result. Yeah, this index of fraction is defined in the peak properties, in Strax processing peak properties, line 10. And it's used, as far as I could find, is only used by the compute width algorithm, of which we will hear in a moment, which calls this index of fraction and then uses it for the calculation of the width of the peak. Yeah, so this is it.
Okay, thanks, Andrea. Any questions to Andrea? Okay, I think it was clear, Andrea. Thanks.
Okay, thanks.
So, was there one thing I wanted to mention? No, I don't think so. Okay, so let's move on then. So then we go to.
Can you refresh the page?
Yes. Ah, wow. Okay, Francesco, go ahead.
Yeah. So this is the function that want to compute the width of a peak, starting from this is what I understood. Starting from a decided percentage of a full area. That's mean we have a peak. We want to calculate, for example, the width of peak when we have 50% of area, peak area. Is correct this? So to do this, basically, in the function, you create this array, a vector, that don't consider in the first being the 0%, but just go from the next step to 1. This and then calculate for this array with all the percentage we want. Basically, the index where the index of a peak array where the percentage is reached. As Andrea explained before, basically this provide a vector, an array, where for each value of percentage, we have the index of fraction corresponding to the peak array, and then we can and the accumulating area of this peak is calculated until to reach the percentage of area. It's a bit. So basically, at the end of this, here is as output of this. Oh, sorry. I remove, double click it. At the end of this calculation, as output, we have this fraction time, and then calculate basically the in nanosecond. This is just number of index. You can see in the, I don't know if you can see here. No, there's no. In the fraction time equal to index of a fraction. No, the step next, it calculates this value, this vector for the peak dt that I suppose is the value in nanosecond for each bin of a peak, right? So, and then this last step for me is a bit confusing because I'm not so familiar with the column, the index operation. I still have to take a bit of confidence. But basically, what I understood is he calculated this in the last two row of the code, the width just as a difference between the full peak length minus, no, sorry, I don't understood. So this is a bit more confusing how to calculate effectively then the width. Is the difference between what?
It's fine, Francesco. I think you made clear what the function does, and yeah.
Yeah. In any case, at the end, just to make the sum of each bin calculated until to reach the final length. This is my understanding.
Yeah. Okay. Thanks, Francesco. Any questions on compute width? Maybe to just briefly mention about these indices that Francesco mentioned. So what this, for example, means is that you take all the elements along the first axis, so you don't apply any row-wise selection.
Yeah.
And what this means for the third element here, that's the step size by which you shift through an axis. So in this case, the second axis. So if a step size of -1 means that you reverse the axis, and a step size of 2 means that you skip one element each time.
Oh, okay.
But yeah, indeed, there's probably more documentation on this elsewhere.
Yeah, I tried to get this information quickly.
No, don't worry. Okay, thanks, Francesco. So then I think we've got one more on touching windows by Hongyi. So Hongyi, if you would like to.
Can you hear me?
Yes, we can hear you.
Okay, so this touching window has two arguments, which are things and containers. Actually, there are three arguments, and the other one is a window, which is the default, or which is the length of the window, but its default value is 0. So here is code in the Strax and peaklet processing, and here the hits are the things and the peaklets are the containers. And we use it here to count how many hits there are in a certain peaklets. And the hits are sorted by the time, and for a certain peaklet, Strax will loop over all of its hits and find the first one whose end time is after the begin time of the peaklet window, and mark it as the left eye. And also it will find the last hit whose end time is before the end time of the peaklet plus the windows, and mark it as the right eye. And after we find these two, we will call the numpy.def function to subtract the right eye by the left eye, and thus we calculate how many hits there are in a certain peaklet. Yeah, I think that's all.
Okay, thanks, Hongyi. Any questions to Hongyi? So maybe I should point out that there's one other place where we call it, and this is actually, so I think, Daniel, you added this line, right? That you use touching windows in peaklet processing. Is that right?
Yes.
Yeah, no. So there's one other place where it was used, and that is in the peak proximity computation. So when there's a variable about how many peaks are nearby another peak, that's where this function is also useful. In that case, the containers and the things are the same, which is a bit weird. But then you just look for every peak, like how many peaks are left and right of it within a certain window. Just looking at this, is there an off by one error here? That if you have, for example, two hits overlapping with a peaklet, then they have like index 0 and 1, then I would subtract them and I would get 1. But there's actually 2 hits. So should there be a +1 or?
This might be that I missed this case.
Okay, it's fine. I mean, there's probably more such errors in there. Good excuse for reprocessing everything again.
And advertising tests.
Exactly. A unit test would have ideally caught this. And this is why these other like lower level pulse processing functions, they often have lots of tests because we really don't want off by one errors somewhere deep in some waveform or something that it's like a horrible bugs to trace. This is relatively, I mean, it's in Straxferno. It's not buried too deep. Okay, good. So thank you everyone for these presentations and for there's a few other people who made pull requests that we didn't go through, like changing comments and so on. Thanks for those as well. I don't think I've reviewed many of them yet, but I will get to them. But as my time in Xenon is nearing its end, I get lazier and lazier, of course. So at some point, I hope one or two of you will take up the mantle of Strax maintainership. Things will go faster again. But yeah, the fact that all of you are engaging in this way already with Strax, that gives me a lot of confidence that will go okay. So good. Right, let's get back to our slides for today. So I'm going to give you a brief reminder of where we are and just like maybe 5 or 10 minutes demonstration of some mini analyses, because there's no tutorial covering it. And there are several useful features that maybe are missed. And then the time we have left for any questions you had on this week's reading on data loading and mini analyses, which we'll discuss. If there are more questions that we can't get to, I'm certain one of the next lectures, maybe next week already, we'll have some more time. Now that there are no big homework presentations to go through. So this is something I presented at the start of the course. It's actually already a very old diagram, but it shows you just the structure of Strax. So you have the user here at the front, the context, and here the plugin classes. And that's where we spent most of our time up till now. Also, all the algorithms that you heard about, they're not directly in the plugin classes, but are called by the different plugins. So this is very much on the sort of physics side of the whole operation, how that works, and yeah, just how the data is actually processed. Most of the rest of the course is going to be about everything else. So like how do different parts connect, how does it relate to the storage system, how does things relate to metadata, and how is the data flow inside the processor. So you can also see that in terms of the circles. So we started here, we've gone through the plugin classes, and this week and next week we're going to talk about some aspects of the context, specifically so the mini analyses and the data loading this week, and next week some aspects of metadata and run selection, configuration that are more internal but are still relevant, I think, to many analysts. So I think it's good that we still have several people here. Also, the storage system is what we go next, is something where not everybody needs to know all the details, but it's good that you've at least seen what like a front end and a back end is, what a hash is exactly, how it's computed, etc. From there on, we go towards sort of the inner circles of Strax, and we really go into the details of how does a plugin work internally, how does it communicate with other things, and finally, how do things sort of communicate with each other inside Strax. So I think after this week or next week already, we will no longer be talking about physics algorithms or plots. We're really just talking about software implementations of how these things work. But at least for the next 3 weeks, for this week and next 2 weeks, I still think those things are relevant to many analysts. Whereas I think these things are really only relevant to a few people who want to develop and maintain Strax intensively. At least if they work well. If they don't work well, analysts may start seeing mailbox errors, but let's hope that that does not happen. Okay, so that's where we are. We are in circle 3. So today we're going to talk about data loading and mini analyses. On the data loading, I don't really have much to say. We already covered all the functions in the user interface. So yeah, there we're just on the reading to trigger any questions, and we'll go through that in a moment. On the mini analyses, I do want to just briefly show you what kind of things you can do with them. This notebook will of course be posted as usual. So let me just show you a few mini analyses in use. So here's a high level one. Oh no, it's going to do other stuff, but okay. So plot energy spectrum, you can feed in a run ID. In this case, I took an argon run. I also have a background run here in reserve. And you just immediately get an energy spectrum. So that's really the goal of these mini analyses, that there's some very quick command that if you have some run that somebody acquired, you just quickly want to check what's in there, you feed it into these mini analyses and you don't have to copy paste large bits of code, etc. So that's mainly the goal. You can customize things. For example, what I do here is I call 2 of them after each other. One for the argon, one for the background run. I give it a couple of options which are passed to the plotting function, like this color and label. I give some options like this, which have nothing to do with the plotting, but which are used inside plot energy spectrum. And I hope I added a docstring for this. It's always tricky with mini analysis. Yes, I added the docstring, great. So you can see that there's a parameter min energy, max energy to control the minimum and maximum energies of the histogram, number of bins, etc. I can specify another unit and events per bin. Then you do have to give the total exposure. Don't know why it's in kilograms seconds, but okay. And then you get some plot like this. Also, there's a selection string here. Tim, you had a question.
Yes, suppose I want to also plot Monte Carlo now.
Mm-hmm.
Is then the Monte Carlo also does this have a special run ID in the end, or do I get returned the bin content somehow? What should I do?
Yeah, good question. Not only will it have a special run ID, you will also need to load a special context, because this context is configured to load data which has produced by the DAQ. So if you ask for some run, it will ask for the DAQ data of that run, whereas you will want the Monte Carlo data for that run. So you'll load a different context. We have a few. Let's see, there Strax contexts. Then there should be Xenon and some simulation, something like this. No, there isn't. Maybe there's one ton simulation. Too bad. Yeah, okay, maybe there isn't an official simulation context yet. I thought there was one though. Anyway, context file is on the reading for next week, so you can. Okay, so let's not go through that now. But there is, or there should be eventually, a Monte Carlo context. So then you can load that context, store it under ST2 or something, and then just plot here ST2 plot energy spectrum.
Okay.
Yeah, that's the idea.
But this still wouldn't allow me to plot data and Monte Carlo data in the same plot, isn't it? As long as I do not return the data somehow.
Yeah. Okay, so for mini analyses, mini analyses only work with one run at a time. But surely, if you want to do something more complicated, you load the data from both, and then you make your own plot. That's totally fine. Yeah. I would have them here in the same plot because this mini analysis plots on the current plot. So in this case, the second time you call this, it will plot on the one that's created just for the argon run. So if you call only this one, you get this, and then the second one plots on the same plot. So that would work. Okay, other questions on what I just showed? Okay, so mini analyses, the idea is just to have a quick thing that you can plot. Usually output is a plot, but it doesn't have to be. It can also be something else. The ones I'm going to show here are all plots. Here's another important one, waveform plotting. There's actually 2 mini analyses for waveform plotting in Strax, but only one works, at least at the moment. There is also this waveform display. Maybe it works sometimes. For me, it didn't currently. I think Chris also reported a different error. It's more complicated and harder to maintain. So at least for the moment, this is the display that we have. For all mini analysis, you always must give the run ID. And then there's a set of options you can always give, like time range or selection string. And sometimes they have other special options. And sometimes, if you're really lucky, those are even documented. So in this case, that is actually the case. There's again a doc string, but there are others where this is not the case. Then you just have to look at the source. So plot waveform just plots a waveform. It isn't very fancy. It would be nice to expand this a bit, perhaps to maybe show like the areas of the peak, or also show the hit pattern. I thought we had something like that. What is it called? Event display or plot event? Or, no, maybe not. Maybe I looked into it once but never made it. Lots of nice projects to do here. Let me just show you how that might work. So suppose you want to extend the mini analysis or make a new one. One thing you could do for this waveform, it's a pretty interesting waveform, by the way. Anybody, any idea what this could be? Looks a bit odd, right? It's a big S1 and it's sort of like...
Is it a muon or what?
Exactly, Matteo. It's a muon, right? You see these very long, long S2-like signals. That's kind of a... This is all Xenon 1-ton data. It's a classic signal of a muon. At least that's what I think it is. It didn't come with a label attached, of course. And you notice that there's these gaps over here. That's a little interesting. Why would it suddenly like cut off? Anybody think of a reason why that might happen?
Is it that cut outside hit part of the hit finder?
Sure, that would be one possibility. So that will cut when there is no signal. So that would mean that there would be no signal here at all, basically, but the PMT still registers something. That's possible, but it looks like there is something then afterwards. So why would there be no signal here and then it starts up again?
High energy veto.
Exactly, Chanyu. It's the high energy veto. But that's more than a guess because you can actually plot that. So let's extend the mini analysis to do that. So here's a very simple plot vetoes routine. Just normalize the time and then there's an XV span for time and end time. So I get the veto regions, which contains that information. And then I call plot vetoes, which gives me just little red regions where the veto is active. So you see indeed that it is the veto that's blocking this. Okay, nice. Now, how do you extend the mini analysis to do this? Right, so here's just an example. So you define a function and you decorate it with this Strax and mini analysis thing. And a decorator just is something that takes another function and outputs a different function. In this case, you actually have something you might call a decorator generator, since you must first call it and that returns a decorator which modifies functions, but don't get too hung up about the names. So you can pass some options here, like what does it require? Yeah, that's pretty much the only one that matters. The only other one you might consider is this warn beyond second. If you have a mini analysis that loads a lot of data, it's kind of nice to have this warning so that if somebody tries to plot too many seconds, it will just give the warning as opposed to crash the kernel. So then you can have a variety of... Sorry, do you have a question?
Yes. Can you remind me how we implemented this high energy veto? It's hardware veto in the sense that data is not recorded at all, or there is some tag and then during the processing we take out all the records that fall in this period?
Yeah, it's a software algorithm. So you can see more details about it in Sophia's note. I think we linked that in the readings for last time. Otherwise, I should link it. There you can see exactly how it works. There's a complete description. But it is in software. Yeah.
Okay, thanks.
Okay, so here I name my function just cool waveform display. I can give it a variety of arguments like context, run ID. You'll have seen those in the reading. Those will be automatically filled in by Strax if you call the function. Another one of those is t-reference, which, unless it's passed by the user, will be set to the run start time. And your veto regions is, of course, the thing that I actually need. And these other keyword arguments I pass on to the this plot waveform. And then you just write your function, and just by having this decorator, it will immediately be sort of registered in the context, and that's it. That's all you need to do to add a mini analysis. So in this case, of course, you would not add a new mini analysis just to do this. You would just add this little thing to the existing waveform display. But yeah. Okay, questions about that? Right, let me just show you a few more mini analyses before we go to the questions on the reading. So we also have some on lower level plotting. So here's this thing called plot records matrix, which will give you the PMT waveforms in every channel. There's also a variant which is just called records matrix, which will actually, I hope there's a docstring, yes. So this will actually return the waveform matrix. So in case you want to make a more detailed plot, say for PMT 41, then you can use that. You can also plot the raw records. You need to do plot raw records matrix. Well, at least that's what I thought. Oh no, it's, sorry, you passed the raw equals true option. I shouldn't second guess my own notebook. And then it will load raw records. And the difference is the option that Louisa mentioned, that this cut outside hits is not applied yet to raw records. I don't know why it's. Oh yeah, maybe I should have done that. Yeah. I was now trying to plot this for this window, which is way larger. That'll work probably, but it takes a lot longer. Right, so you see here that in the raw records plot, there's all of this black stuff. That's what's cut by cut outside hits normally, and not this time. So see that there appear to be these regions with gaps, so that's a bit odd. This could just be that these are outside, just the last item on the map, or there might be some other problem that we need to debug. You can often see this when the window that you put in is a float. Then you will get completely nonsensical answers. So be careful not to do that. But in this case, I don't know why there are these white regions. Maybe it goes into ADC saturation. It wouldn't be so odd for a new one. You can also plot them together with plot waveform. Yeah, it's just you pass deep equals true.
Seems all the bottom array made the same.
Yes. Yes. Okay, so we also have an event scatter plot, which can be nice, but you've seen this in the tutorial, and we have some for peak level analysis. Just plot a quick histogram of all the peaks in the run, or the classification. And just to show you again, if you want to apply a selection, so suppose I wanted to apply a selection string here, say n competing less than 1, it's going to fail. It says, hey, n competing, what's that? I don't have that. That's not part of the data that it's loading. It's just loading peak basics, but n competing is in peak proximity. You can still use the mini analysis. You just have to load the data yourself first and then pass it on to the mini analysis. And that's another way you can use it. it does work, but you have to go one extra step. Okay, I hope that wasn't too basic, but just to give you a demo of what each analysis does, so you know which one to use. And I hope that as we progress in Xeno 1.1, several people will add their analysis as a mini analysis, because especially for exploratory data analysis, it's nice to just be able to plot an energy spectrum with a matrix of or a histogram of peaks just to see what happens. Any questions on that?
I have a small question. So these mini analyses are more like useful functions, I would say, like transversal to kind of all of studies, but something a bit more complex, like you give it a run or a set of runs and it gives you some properties, things like electron lifetime or some correction maps, whatever. Does this make sense in mini analysis or proper studies, let's say?
You can. At the moment, the only restriction is that they, well, at least I think, maybe I once tried to implement, but I don't think I saw that it only takes one run at a time. So if you have something like a correction map fit to a whole bunch of Krypton data, yeah, then it doesn't make that much sense anymore. But yeah, they're sort of an intermediate between something you write in a plugin, which is more low level, like for every peak you do compute something, and a full analysis notebook. There's something for one run, a quick plot or a quick check, or yeah, maybe you can fit, you can do an electron lifetime fit with it. That would be fine. But you would not put in the electron lifetime evolution model, for instance.
Exactly, thanks. At the same time, like quick checks of those things. Okay.
Yeah, that's what they're meant for. More questions on this? All right. So
yeah. Oh, sorry.
Yeah.
I
Go
was
ahead.
muted.
Sorry.
Just a question. To use this plot peak, this kind of function, we need to load some particular plugin before, or he able to choose alone which is necessary to do it?
Yeah, so that's part of the idea about mini analyses, that when you do this, you don't have to specify like which plugins you need to load. That's encoded in the mini analysis. So the mini analysis says here, let's go to this example, I require this, and then Strax will load that when you call that. As a user, you don't have to specify that.
Okay, yeah, no.
Yeah.
Perfect. Thank you.
Mm-hmm. Okay, I see then that we shamefully have only 15 minutes left for the questions and discussion, so we should definitely take a bit more time to go through all of the material you read. I think next time we'll have a bit more time. But let's just start at the let's start with the data loading, and then we can get back to mini analyses maybe next time. So let's see what exactly we had on the reading. So we had this next time. Here, context.py. Yeah, okay. So apply selection, make, get data frame, get array. Okay, so those are in Strax. Context.py. Okay. Right. So did anybody have a question on either of these functions that we can talk about? You can try to unfold them to try and refresh your memory. We had apply selection. We had make. Get array. I don't think accumulate was part of the reading, right? That's a pity. There's a nice Yeah, anyway, and get data frame. Okay. Any questions on this?
I had one on one of the reading questions.
Sure.
Yeah, I just couldn't answer why we do that for loop that just does a pass.
Mm-hmm.
So
Yeah.
I don't know if we could go over that.
Okay, sure. Let's look at that. So that's in make. So here in make. So that's this for loop, right? So we do get iter, and then it just passes. Yeah. Yeah. So that's okay. So maybe the first question: how would we rewrite this as a list comprehension? Anybody have any idea? Or do you want to take control of my screen to do it? I set it to accept all requests. So if you feel you ever wanted to control my screen, now is your chance.
Sorry, can you repeat the question?
So the question is to rewrite this as a list comprehension. Because it's a bit odd, right? You do a for loop and then pass. But why
You mean a list comprehension like it is there?
Well, example of the list comprehension is a bit lower. So I could go
You mean
over
just really writing this for loop as a
Mhm.
list comprehension?
Yeah.
Does this now work? Can I do things?
Yeah, it works. Somebody's typing.
Yeah,
So it's you, Peter.
I'm trying. So, well, yeah.
Ah, you can do pass there. Yeah, that could even work. Yeah.
Yeah.
But basically, most of the.
So it's a bit odd. Well, shouldn't you technically do an generator comprehension? So you should use round brackets instead of rectangular ones, right?
Okay. Why are you proposing that?
So this get iter guy, it's a function, but it doesn't return. It returns a generator object. So if you look at where the definition is, it doesn't say return, it says yield.
Yes.
And then it gives a generator, and that's not something which is fully calculated. And the reason why you do this is because you can save a lot of memory. Now I'm completely lost where I was typing. So that's also why you pass, because you're not interested in executing the generator. You just wanted to loop over all the guys and then continue with whatever you were doing.
Yeah.
So it's almost just like making sure everything is there. So it will always run unless there's something broken inside get iter.
What do you mean?
Like, will this always work? This is just kind of a guarantee.
Well, if you make a mistake, it should crash, right?
Right. Okay.
But it's a trick. It doesn't give you the complete data. So if you would store it in something, you cannot access like a value. So here you get this result stuff, and here you can access data or area or whatever. And here in this generator guy, you cannot do that. So you first need to loop over it before you can actually access the data. And since with make, we're not interested in directly accessing the data, we just want to create it. We don't need to iterate over it.
Okay, so you're right. So get iter is an iterator. So whenever you iterate over it, you're going to get stuff. But the stuff that you get here, thanks, Peter. I think this is clear how you would rewrite it. So you have, so this code is, I think, equivalent to this, with the one exception that you hear a return a list with nothing in it. I don't know if this actually runs with pass, but you could also put a 0 in here. I mean, it doesn't matter. I guess the gist of the question maybe wasn't phrased so clearly, is why wouldn't you do this?
Okay. So you're just saying because we don't want to store the data.
Exactly, that was it. So if you
Okay.
were to do this.
All right, that makes sense.
Okay, yeah. So that's the entire idea of it. That here you just, I don't want to store the data, so that's why I do nothing inside the for loop. If you do nothing inside a for loop, a list comprehension is really weird, even weirder than a for loop with pass. Yeah.
Gotcha. Okay, thank you.
So basically, all the work is done already by getIter. This is just a way to force this work by getIter.
So it like forces
we
the
don't need
generator.
anything out of that.
Yeah, so getIter doesn't do anything. So that's what you see over here. So I just assigned that to source, but that didn't actually iterate over anything. That just, okay, now I'm a generator. I'm not going to do anything until you call next, or if you start iterating over it. And that's what happens here, and that's what happens here. And Peter was actually suggesting that you can add a generator expression, so then you can have, but then you would generate another generator that you would have to then iterate over again to make that happen. So you can do that. I've rarely used generator expressions myself, but they're a cool feature for some things. Maybe they are used somewhere deep in one of the lower circles. I wouldn't be surprised, but we'll get that then.
Okay, thank you.
Okay, other questions about these functions?
Sorry, Jelle, I've got a more basic question. What's make used for?
What's make used for? Yeah, it looks pretty useless, right? It doesn't return anything. It just loops
know.
over the data, spends a lot of time, and then you still got nothing. So does anybody have a use case for make?
Reading stuff from the DAQ.
Make stuff from the DAQ. What do you mean, Joran?
So when the DAQ outputs like the raw stuff that comes from the digitizers, it's even so raw that it's still alive. That's why we call it live data. And we don't want to ship out all this stuff. We want to process it to Strax format. But we don't actually want to read anything of these data. We just want to make raw records, peaklets, whatever, and then ship it off rather than having this live data being transferred to DALI. So in that instance, you would make the data rather than read it. So then make is a perfect example, a perfect function to use.
Yeah, exactly. So it's used for making data you don't want to load into memory. So one case is what Joran mentioned, you're the DAQ, you want to process data, but I certainly don't want to load all raw records into memory, then I will explode and die. I just want to know that it has been created and can be shipped. One thing you might encounter in your own analyses is, suppose you want to make some kind of time range selection, then Strax will actually, I can show this briefly. Suppose right here I'm loading event info, but suppose I'm loading it with another option. So some option S1 min hits equals 16. I can do that. Well, I need to pass a valid option. Name me an option. Trigger min area. That looks like an innocuous option. Let's try that one. Trigger min area. Right, I can do this. Then I get the data back. But for lower level data, you may not want this, because then if you load all the data, it will blow up your memory. So if I try for raw records or something, that won't work. You want to load some kind of time range, right? So suppose you want here seconds range 20 to 30. Let's set this to something. It will give you an error. It says, hey, your data is not available. And I refuse to do time selection until the data is available. But if this is raw records, then I can't just do this and get all the data into memory. That will then blow up. So that's when you call make. So then you will first do make, and then you do the load with the time selection that will prevent your memory from going into trouble. Okay, well, that almost worked.
Oh, as in, like, I thought in the first lesson we learned that we can use like the seconds range and a lot of other stuff to reduce the things you want to load in. So
Yeah.
will that work even without make?
No, seconds range only works if the data exists. So you can use it if the option, if you don't specify any option, the data is already built. But if you want to use seconds range on data that isn't there yet, you have to make it first.
Okay.
Yeah. I don't know why this option, this now didn't work. Maybe one of you saw a stupid thing that I did to her.
So it's kind of like instantiating it, right? Even though there's no such stuff as instantiation in Python.
It just makes it so there'll be now in Strax data here, folder, event info. We'll look at this in 2 weeks, where there is a, which was created with this particular option. I guess the trigger min area goes to events here. Yeah. Okay. Okay. More questions? We've got time for one more. Then we'll come back to this next week. Let's take one of the study questions. So how about this one? Get array. You have here a selection string option. It's actually part of the quarks, so it's not applied here in get array. What's the use of that? Why can't I just apply like a fiducial volume cut after I get the data? You have to apply it sometime. What's the point? Is there a point? Maybe there is no point.
Well, selection string applies the it applies the cut as it loads chunk by chunk, and as opposed to if you try to load all of it into memory and then your kernel crashes before you have the opportunity to make the cut yourself.
Yeah, exactly. That's it. So selection string along with time range and all of the other options that go into this quarks, they're used in get iter. I don't think get iter was on the reading, but I'll just briefly look at it. There will be here, this folding is not so useful. Here, there's apply selections. This is done chunk by chunk. So for results, for every part of this generator, it will apply the selection. It will also apply the time selection. This folding is really bad. Yeah, so that's the answer. It saves memory, and it's quite a bit convenient as well, but mostly for saving memory. Okay. Good. So I think we're getting close to our time now. So let's just briefly look at what's on the menu for next week. So this week we looked at loading data. Next week you're going to look at various things to do with metadata and just registering of plugins and selection of runs, things like that. So you'll look at this context object, what it really is, how do you initialize it, what are the kind of options for it. You'll look into, this is very brief, just how run selection works. There's just a couple of helper functions. There are many other ways you could do run selections, but this is a helper that you might like. And then configuration, which is important if you want to make your own plugins to at least have some rough grasp of how this works. Both of these things, there is already a tutorial on, so review those first before you dive into the code. Yeah, then you'll learn the different kinds of options that you can set, what they mean, yeah, what sort of things they can do. And there's actually here an exercise to implement a feature that's not there. So the first person to get there may open a pull request and get a useful extra feature added to Strax. And we'll try to get to the other questions that you prepared for this week, but we didn't have time for as well. Okay, any questions, comments before we close? Okay, very good. Good luck with your reading for next week, and we'll talk to you then.
Thanks.
Bye.
Bye-bye.
Thanks.